Good morning and welcome to the webinar, Hermeticity Testing for Military and Medical Microcircuits. This is the first in a four-part series. Today's webinar is titled A Reason to Seal. And hopefully everyone can hear me. We have a number of people on the line, and again, welcome. This session, just as a reminder, is being recorded. I'm going to ask for today that you save your questions till the end. You can submit by raising your electronic hand, or you can text me on your control panel. Either way is fine. At that point, I'll unmute you, and we can ask the question, and hopefully everyone will be able to hear me. Just a couple of words about my background. I'm Tom Green, the instructor and moderator for this series of webinars. I've been in the industry approximately 30 years. Worked a number of years at Rome Air Development Center, which was a Air Force research lab responsible for the military standards, Mil Standard 883 in particular, and the one of our which is very important to us, test method 1014. I also spent a number of years in industry with Lockheed Martin, building essentially complex hybrid, hermetically sealed hybrid microelectronics for military and space applications. And for the past 10 years, I've worked at T.J. Green & Associates, where I spend about half my time teaching webinars, public courses on materials, processes, hermetic sealing, and also a number of consulting projects focused on hermeticity and other aspects of manufacturing devices, hermetically sealed microcircuits for military and medical implantable applications. This is the first, as I mentioned, in a four-part series. Today's session is A Reason to Seal. We'll focus on the definition of hermeticity, why it's important. I'll talk to you a little bit about the various ways of hermetically sealing a microelectronic device. Then we'll look at the equation that relates moisture ingress into a hermetic enclosure as a function of time. And hopefully I'll have time to also speak to residual gas analysis and the test method 1018, which is the cousin, I guess, to test method 1014. Session 2 is focused on 1014, which is the de facto standard for hermeticity testing. We'll go through the basics of helium mass spectroscopy, both the fixed and flexible method, also known as the Hahnemann equation, and review the various techniques for gross leak testing. Excuse me. Session 3 is focused on 3 leak testing techniques in particular. The first is optical leak testing technology. Second one being cumulative helium leak detection, which is an extension of the existing helium-based hermeticity test methods, and Krypton 85 testing. Each one of these techniques is capable of making very low leak rate measurements, and there's a lot of interest in some of these newer techniques, so we'll spend some time delving into the details of each of those. Our final session looks at the recent changes to 1071 and the impact that has on the community, the impact of a tighter leak specification, and also touch on some potential options and alternate procedures for assessing hermeticity and moisture ingress Specifically, I'll talk to you about moisture sensing, which is a topic that I'm near and dear to, and I think holds a lot of promise for the industry. The information for this series, this webinar series, comes from my own personal experience, plus technical societies like IMAPS. This is the International Microelectronics and Packaging Society. Maybe not so much SMTA, but IMAPS and IEEE each year present technical papers and regional and local meetings where they discuss hermeticity and various aspects of hybrid packaging, die bond, wire bond. Each year in upstate New York, there's a meeting that goes on. It's titled Minnowbrook. That's the name of the camp where we meet, and it's an informal gathering of 30 or 40 individuals from the industry getting together to discuss the standards and the issues associated with hermeticity and moisture ingress and epoxy outgassing and those kind of things. If you're interested in attending, just send me an email and I'll be sure to get you an invite. This website, DLA, is the place to go to download the specs. I'll be referring to Mill Standard 1014, Mill Standard 1018, and Mill Standard 1071, which is part, or Test Method 1071, which is part of Mill Standard 750. Every year, or not every year, a few times each year, the Electronics Industry Association and JEDEC get together. This is Joint Electron Device Engineering Council. They have a website that also has a lot of good information on hermeticity and test methods. The book, the textbook that you should all invest in, is called Hermeticity of Electronic Packages by Hal Greenhouse, and it's an excellent treatment of the subject. You can get it off of Amazon.com for a reasonable amount of money. I also have access to a lot of old RADC reports, and on my website, tjgreenllc.com, you can find 2 white papers. One is a practical guide to 1014. The other is a recent publication I just posted a few weeks ago, which lays out some of the arguments of hermetic versus near hermetic packaging, which is getting to be a very important and interesting topic within the community. Okay, let's get started here. The picture you see on the left is a typical hermetic package. It's made from glasses, metals, ceramics. This happens to be a device that's commonly used in the telecommunications industry, a butterfly package. Here's an example of a complex hybrid that's made from a Kovar package that has nickel and gold plating on it and glass to metal feed-throughs that provide a hermetic enclosure when sealed, seam welded, laser welded. When I speak of non-hermetic packaging, in my mind, this is referring to plastic ICs, which have are widely used in commercial applications and in some high-rel applications. These are plastic molded parts, and the concern here would be moisture permeating through the plastic and attacking the electronics. There is now quite a few options available in what I term near hermetic cavity style packages. Packages made from materials such as liquid crystal polymers. They still have a cavity. They don't fit the definition of a hermetic package, and applying the existing test methods, hermeticity test methods, to a near hermetic package has to be done with great caution and is a topic for another day. So what is hermeticity? The dictionary definition of the term hermetic is simply a gas-tight enclosure impervious to gas flow. Keeps out the harmful gases. Also, unfortunately, keeps in some harmful gases. But the key to hermetic is that it's a package made from metals, ceramics, or glasses. It's not made from polymeric materials. In the testing that we employ, we disregard the permeability of gases through the metal, the glass, or the ceramic. And that's because they're so low that they can rightfully be ignored. So in a hermetic cavity, if you can create a seal in a dry atmosphere, typically inside what they call a glove box, a nitrogen purged or nitrogen helium mixture environment with an extremely low dew point, practically zero moisture in the cavity. If you can do that, then you can seal the part with a sufficiently low leak rate. It'll keep it dry and moisture free for many years, and provided it doesn't continue to outgas any moisture from the polymerics that may be used inside the hermetic cavity, then you have a device that's going to be robust to any moisture-related failure mechanism. So for our purposes, hermetic means it passes the mil spec. In my mind, specifically 1014, but 1071 as well. We'll talk about that here in a minute. The hermeticity specs, by the way, are tied to a particular package volume, and it's based on an air equivalent leak rate. Okay, and that's an important thing to keep in mind. So why does a package need to be hermetic? There are many failure mechanisms and reliability problems that have occurred over the past 30 or 40 years in both medical and military applications that are directly tied to moisture, and specifically moisture that condenses out onto the surface of the component. Any CMOS chip made today, most of them have aluminum metallization still, although they're moving to copper. And that aluminum is exposed at the wire bond pads. So if a droplet of water were to form on the surface of the device near that exposed aluminum metallization with ionic contamination and a bias, you would take the aluminum metal into solution and corrode the bond pad or corrode the aluminum wire connected to the bond pad. You can also experience other anomalies, electrical anomalies and failures when you have surface conduction. It's pretty well agreed to that 3 monolayers of moisture, water molecules on the surface of a device is enough to support conduction, electrical conduction, which can cause failures. MEMS components are particularly sensitive to moisture and a phenomenon known as stiction. Silver and gold are metals that have been known to form dendrites. Silver in particular, the silver that's in most silver epoxy is prone to grow dendrites and cause shorts along the substrate. Passivations have gotten much better on chips over the years, but still if there's pinholes or defects in surface passivations, then again you have pathways for moisture to attack and damage the devices. Moisture droplets are formed as the package is cooled below the dew point, and then within the device, if you're above 5,000 ppm, let's say, you can form moisture and have these problems. Here's a good example of a failure that occurred, fortunately, during qualification. It's an unpassivated nichrome chip resistor. and these are especially susceptible to failure. And right in this area is where the corrosion took place, caused the resistance to increase and the device to fail.